the video for online lesson number 5. The first 10 slides are going to be a review of what we were working on before spring break. The last few slides are new. So just a quick review of what we were doing, finding the 6 exact values on a unit circle. For this one, the angle of 135 degrees was provided for us. So we're going to go ahead and locate 135 degrees on our unit circle. Again, that's equivalent to 3 pi over 4 radians. In terms of finding the 6 exact values, that coordinate gives us 2 of them. Cosine is your x value. Sine is your y value. And tangent is y over x. Make sure you reduce your fractions. To find the other 3, we're going to take the reciprocals of these. The reciprocal of cosine is secant. This one needs to be rationalized. Next, we'll find the reciprocal of sine, which is cosecant. Again, rationalize. Cotangent is the reciprocal of tangent. And those are the 6 trig ratios. For our second example, let's remember that if we go around the circle counterclockwise, we use positive radians, positive angles. If we go around the circle clockwise, we use negative radian measures, negative degrees. So for starting at the beginning, going negative 120 degrees, we're back here in the same place as 4 pi over 3. Cosine is your x value. Sine is your y value. Tangent is y divided by x. Again, on this one, when you're dividing a fraction, remember you have to multiply by the reciprocal. The 2's cancel out, the negatives cancel out, leave you with root 3. To find your reciprocal functions, you need to flip the existing functions you have. The reciprocal of cosine is secant. The reciprocal of sine is cosecant. This one needs to be rationalized. And then the reciprocal of tangent is cotangent. This time that's x divided by y. Again, you're going to need to multiply by your reciprocal. The 2's cancel out, the negatives cancel out, and then you have to rationalize. For the third example, remember that the circle is continuous and you can keep going around the circle as many times as needed. So if we want to go 930 degrees or 31 pi over 6, one full circle is 360 degrees. So we're going 2 full circles and 210 degrees more. It's going to put us down here into quadrant 3 at 210 degrees. If we think about the same factor with 31 pi over 6, you're going to look at your 6th which happen every 30 degrees, and you're going to count a total of 31 of those. Or look at the fact that 2 pi radians, or 2 full revolutions, is equal to 4 pi radians, and you can subtract that from the original. Once you figure out where you land on the unit circle, then you can find your 6 trig values. So cosine, again, is the y value. Sine is the x value. And tangent is y divided by x. These are going to be similar to the previous ones except reverse. So on this one, when you take tangent and flip it, you're going to end up with root 3 over 3. The reciprocal of cosine is secant. Again, rationalize. The reciprocal of sine is cosecant. And the reciprocal of tangent is cotangent. For our next one, we want to find an angle given the coordinate. When we look at this, we know that sine is a y value. And it tells us it wants somewhere in quadrant 3. So we're going to find a y value of negative 1/2 in quadrant 3. And that tells us that theta equals 7 pi over 6. How we want to think about that, again, if we have sine of theta equals negative 1/2, we're solving for theta. So by solving for theta, we're taking inverse sine of negative 1/2, and that gives us to the appropriate angle. If the directions change, so now we're looking for all values between 0 and 2 pi, then we want to think about the fact that every point on the unit circle happens twice. So now we're not just looking for the y value of negative 1/2 in quadrant 3, but we're looking for both places on the unit circle where our y value equals 1/2. Again, this time, you have sine of theta equals negative 1/2. You're solving for theta, again, inverse sine of negative 1/2. And you're going to make a list of both places where sine theta equals negative 1/2. Your answer would be 7 pi over 6 and 11 pi over 6. So there becomes 2 answers as we're looking for the interval or domain between 0 and 2 pi. That's 1 revolution. Let's look at tangent of theta equals negative 1. Again, our domain is between 0 and 2 pi, so we're looking at 1 revolution. Since tangent is y over x, in order for that to be equal to negative 1, both your x and y coordinates need to be the same, but one of your values needs to be negative. So that happens in quadrant 2 and quadrant 4 when we have the x and the y value the same, but one of those is negative. So when we isolate theta, that means we're taking inverse tangent of negative 1, and your answer is going to be 3 pi over 4 and 7 pi over 4. Now, even though cosecant is not on our unit circle, we can think about what cosecant really is. So cosecant of theta equals negative 1. The reciprocal of cosecant is sine. And the reciprocal of negative 1 is still negative 1. We flipped both of them. So really what we're looking for here is where inverse sine equals negative 1. Remember that sine is a y value. So So we're looking for everywhere on the unit circle that our y value is equal to -1. This only occurs one time, so even though we're looking at one full revolution, theta only has one answer of 3 pi over 2. So this time we're looking for a new value. Now we're looking for all real numbers. We're still trying to find an angle, but we want to incorporate not just one revolution, but all revolutions. It's going to give us all real numbers. So as we look at sine theta equals √3 over 2. Again, we're solving for theta, which is inverse sine of √3 over 2. Sine is a y value, so we're going to look in the unit circle for where our y value is √3 over 2. That happens in quadrant 1 and quadrant 2. When we look at these 2 points, from here to here is 60 degrees, and from here back to the first position is 300 degrees. Those are not evenly distributed around the unit circle, therefore we need to list each answer separately. So we're going to say theta equals our first answer, which is pi over 3. And we're going to add that full revolution to the end, which is 2 pi. And so that we get all real values, we're going to throw a k at the end. Remember, k represents integer solutions. Then we're going to list our second answer, which is 2 pi over 3. Again, one revolution to get back to that. Throw in the k so that we get all revolutions, all places that this exists. Let's do another one of those for all real numbers. For cosine theta equals -√2 over 2. Again, we're solving for theta. It's going to be inverse cosine of that -√2 over 2. So we're going to look, cosine is an x value. So we're going to look for a place on our unit circle in which our x value is equal to -√2 over 2. That happens in quadrant 2 and quadrant 3. Therefore our answers should be 3 pi over 4 and 5 pi over 4. Again, these are not evenly distributed around the unit circle. From here to here is not the same as that to that. Therefore, both of our answers are going to be separate. So we're going to list our first answer. It's 3 pi over 4 plus 2 pi k. And then our second answer, 5 pi over 4 plus 2 pi k. Let's do one more. All real numbers. This time we're doing secant. Again, remember, secant is not on our unit circle. We can see that that was rationalized. So if we unrationalize that, we would have gotten 2 over √3. The reciprocal of secant is cosine. And then I have to flip both sides so that I can take the reciprocal of both sides. Now I have a x value if cosine equals √3 over 2. I'm looking for inverse cosine of √3 over 2. We're going to locate, again, cosine is an x value, so we're going to find an x value that's √3 over 2. That happens at pi over 6. Our second time that it equals √3 over 2 is at 11 pi over 6. Looking at those again, they're not evenly distributed around the unit circle. Therefore, each answer is going to be separate. So our first answer is pi over 6 plus 2 pi k. And our second answer is 11 pi over 6 plus 2 pi k. At this point, you guys should pause the video, go practice on lesson online lesson number 5 from WAMAT Part 1. 18 questions, should take you about 20 minutes or so, and then you're going to come back and watch the video. Welcome back. For the second half of our video, we're going to talk more about that inverse trig values. Again, for this, we're starting with a known coordinate, a known value, and we're working backwards to figure out what angle gave that to us. We remember from our work with inverses, we want to start with making sure we have one-to-one functions. There's the definition of a one-to-one function. Since sine, cosine, and tangent are very repetitive, happen twice or 3 times on the unit circle, we want to make sure that we understand these functions are not one-to-one. So let's look at the parent function, and then we're going to restrict that parent function to make sure it's one-to-one. That highlighted domain will be what we label as the principal root. Here is your parent function for sine. How I got this value, this picture, is I unraveled the unit circle in order to see what was happening. If we look at our y values on the unit circle, we start off at 0. At pi over 2, we have a y value of 1. Back at pi, we're back to 0. 3 pi over 2, we're at negative 1. And back to 2 pi, we get 0. So we go 1 time around the unit circle. I could also go around the unit circle counter or clockwise, and then I would be back in here in that negative realm. In order to restrict this function one-to-one, I want to take a chunk of this graph that is continuous, that gives me all y values between -1 and +1, so that I get all values with no repetition. I'm going to take this chunk of the graph. This represents quadrant 4, starting at the 0, going clockwise around the unit circle. This represents quadrant 1, starting at the 0, going towards pi over 2. This makes the function one-to-one, and this is what we're going to refer to as the principal root. So our domain for the principal root is between negative pi over 2 and positive pi over 2. We're using brackets so we get to include those two endpoints on our graph. Our range, which is the y values, is -1 to +1. Again, it's going to oscillate between -1 and +1. Here's your graph for the cosine function. Again, cosine is still going to oscillate between -1 and +1, but this time we're going to start in a different location. Again, think about this as unraveling those points on the unit circle. This is our x values along the unit circle. We're going to unravel them to create a graph. For this one, again, we start at 1, go down to 0. At pi, we're at -1. At 3 pi over 2, we are back to 0. And at 2 pi, we are at 1. This should be represented again on your unit circle if you look at the x values on your unit circle. We want to restrict this function so that it's one-to-one. Again, this time we want to make sure we have all y values represented between -1 and +1 in a continuous fashion with no repeating points. So for this one, we're going to pick this chunk of the graph that gives us all y values from -1 to +1, all corresponding x values, and this is what we're going to use as our principal root. This represents quadrant 1. This represents quadrant 2. So this is our principal root. So our domain for inverse cosine is x is an element from 0 to pi, and your range is the same as it was for cosine. Your range is between -1 and +1. The last graph we're going to talk about is our tangent. Tangent is not symmetric the same way as sine and cosine more. It does not oscillate in the same fashion, although those points are replicated. Let's remember that at pi over 2, which was 90 degrees, your graph was undefined. That's why you have this asymptote at pi over 2, and that asymptote is going to repeat again at 3 pi over 2. If we go counter or clockwise around the circle, this would be where your negative 90 degrees is, and then again, so those dotted lines are representing the asymptotes that happen every at the 90 degrees. Again, what we can see is this graph in here is symmetric. It looks very similar to a cubic function, but doesn't have quite the same symmetry. So when we find the principal root, we want all values to be represented with no values getting chunked off. So our domain is between negative pi over 2 and positive pi over 2. This time I had to use parentheses because I cannot include those asymptotes. My range is actually all real numbers, as those graphs are fitting into those channels. Those y values are going to approach those asymptotes. There's two different ways that we can talk about using those inverses. The other way we can talk about it is using the word arc. In your assignments, both in the textbook and in WAMAP, they're going to oscillate between these two vocabulary words. So you can either do sine negative 1 power, which again represents inverse, or you can use that word of arc in front. They both mean the same thing. They both mean that what we're doing is solving for that angle theta. So let's take a second and add what we just learned about principal root to our existing unit circle. We know that the principal root for sine is quadrant 1 and 4. I also know that the domain for sine is between negative pi over 2 and positive pi over 2. So I want to go ahead and label those points on my unit circle. Starting at 0, if I go clockwise, that first point I get to would be negative pi over 6. The next point I get to is negative pi over 4. The third point is negative pi over 3. And the fourth point is negative pi over 2. Now both our domain is represented and our principal root is represented with those numbers. The second principal root that we learned was for cosine. Cosine was quadrant 1 and 2. And our domain for that was between 0 and pi. So all my values should be somewhere between 0 and pi. I don't have to add any negatives to this because I'm looking at that positive chunk, quadrant 1 and 2. Tangent is going to be the same as sine, so quadrant 1 and 4, but remember that tangent does not include the negative pi over 2 and the positive pi over 2 because tangent is undefined at negative pi over 2 and at positive pi over 2. When we're looking and evaluating arc sine or inverse sine, we really want to focus on this region that's highlighted, and that way we make sure we get our answers correct. So let's go through a couple examples, again just working through that vocab. Here I have inverse sine and sine. Those are opposite operations, those are inverses of each other. They undo each other, therefore I just get 30 degrees. The next one, again, arc cosine and cosine. Those two are inverse operations. They undo each other, and therefore I just get the pi over 3. It is important that we keep the units the same. If we start in degrees, our answer should be in degrees. If we start in radians, our answer should be in radians. Here, this one went backwards. This time we're taking the sine of an arc sine. Those are still inverse operations, so you get your original input for your final answer. Next example again, cosine and inverse cosine. Same thing, we are doing something and undoing it with that inverse and cosine, giving us back our original angle. A last example here, again, arc sine and sine cancel each other out and just give you negative 2 pi over 3. Not all of these are going to cancel each other out. You can see on our first example on this page, we have a tangent of an arc sine of negative 1/2. We need to follow our order of operations, so we're going to do what's inside the bracket first. If we're finding the arc sine of negative 1/2, we're looking for the y value that's negative 1/2, and then we're going to use our angle. Remember, this represents negative pi over 6 if we're looking at our principal root. So what we're going to actually do is we evaluate the inside of those brackets. Is what we really want to find is tangent of negative pi over 6. Your tangent is your y divided by your x. Dividing two fractions, you're going to multiply by your reciprocal. And that's going to require you to rationalize. You get root 3 over 3. For our second example, we want to start by finding the cosine of pi over 3. Cosine is your x value, so we're going to go to pi over 3. Go to the x value, that's 1/2. Now we're finding the inverse sine of 1/2. Sine is a y value, so we need to find a y value that's 1/2. And that's going to lead us to that x value of pi over 6. So we start here, we move out to the x value, then we jump to a y value because now we want to find inverse sine, and then go to the inside of the circle for our next answer. Let's do one more example on this page. So we want to find cosine of 2 pi over 3. Again, cosine is the of 2 pi over 3. We're going to find the angle of 2 pi over 3. Cosine is our x value. So when we evaluate the brackets, we end up with an x value of negative 1/2. We want to find the inverse sine of negative 1/2. Remember, sine is a y value. So we're going to go down here to find a y value of negative 1/2. We want to make sure we answer the question in our principal root. So our answer is negative pi over 6. Let's go through 3 more examples of how to do this. Again, you want to start on the inside. So this time we're finding inverse sine of root 2 over 2. Sine is a y value, so we're going to find a y value that's root 2 over 2. We're finding the inverse sine of that, which is going to take us to the radian measure. So we evaluate inverse sine of root 2 over 2 to be pi over 4. Now we want to work our way to the outside, which is tangent. Tangent is y over x, which gives us 1. Let's do one more example here. Again, we're going to start on the inside, so we're going to find inverse sine of 0. Sine is a y value, so we're going to find a y value of 0. That gets us to 0 degrees. Cosine is the x value. So as we evaluate cosine of 0, we end up with the x value of that coordinate to be 1. So it's important, if we're using inverse sine, to start on the coordinate that's appropriate and work our way to the radian. And if we're doing cosine or sine, we start at the radian and work our way out to the appropriate coordinate. At this point, you guys are done with your online tutorial. You want to go back to warm up and now try to complete part 2. Again, 18 questions.